I actually said this maybe last time, maybe before, that when we speak of locally finite coverings, actually the term locally finite can be applied to to many other things, in particular to any family of sets. You understand? If you have a family of sets, say A alpha, in any topological space actually X, then it is locally finite if for every point X in X there exists a neighborhood U such that only finitely many intersections U with A alpha are non-empty. If this family of sets is a covering, open cover, then we say that this open cover is locally finite. But actually, any family of sets may be locally finite. For example, family of finite sets, open closed sets. Say locally finite family of closed sets F alpha. So again, any family, not necessarily finite or countable or whatever, but it also can be locally finite, right? And I can say the fact is that the union of the sets is also closed. You know that the union of closed sets closed by maximum topology. This is a finite union. Condition of finiteness can be replaced by the condition of being locally finite. This is more or less obvious. Prove this in a certain way. So let F be the union of the sets, and let some point X is not an F. Then, using the definition, we find there is a neighborhood U of X, say that there are only finitely many non-empty intersections U with F alpha. Say only U with F alpha I, where I so many. Then look at the set U minus the union of this F alpha U with I, F alpha I with I, is open since this is an open set with closed set. And this is certainly is contained in X minus F. No point in F belongs to it. If a point in F belongs to one of these sets, then it is deleted. If a point in F doesn't belong to this set, then these intersections are empty. So this actually, the corresponding F alpha has empty intersection with U, and its subtraction doesn't mean anything. And this, if we denote this as V, will be a neighborhood of X in X minus F. So X minus F is open since every point has an open neighborhood, and F is closed. This may be important, and actually it's possible to formulate some other thing. Speaking of locally finite families of sets, we can speak of locally finite family of functions. Suppose that we have now X is a manifold, and we have some family of, say, smooth functions. So let now X be manifold, and F alpha, I can assume that these functions are positive. It is not important. So this is a family of smooth functions. Now, functions have supports. You remember that support of F alpha. We take the set of points where the values are positive, and we take the closure of the set. This is called the support. So support is actually the set where the function is not zero, and moreover, if a point does not belong to this support, then in some neighborhood of this point the function is zero. It is a closed set by construction. Also, the family of this closed set can be locally finite. Why not? I want to say that if F alpha is a locally finite family, then we can speak of the sum. You understand, my family is not finite. It's locally finite, but not finite. And this is an infinite sum. Still, it exists and also smooth, like F alpha. Why so? For every point x in X, there is a neighborhood U, so that only finitely many functions can be non-zero in U. So my sum in U is a finite sum. It's a finite sum of smooth functions. It is also a smooth function. Why not? And hence the whole sum is defined everywhere and is smooth in the neighborhood of every point, which means that it is smooth. So actually, this condition of local finiteness can be used for forming infinite sums. This is more or less all my introduction. To an important and actually very, very simple in some sense, but important subject, partitions of unity. Let me begin with the definition. Suppose that U U beta is an open cover. Now, I say that F alpha, the family F alpha, is a partition of unity. Subordinated. Actually, excuse me. I prefer to. Well, my covering is also U alpha. Partition of unity subordinated to U. If the following holds: first, this family is locally finite. Second, the support of F alpha is contained in U alpha. And the sum is defined since f alpha r is equal to 1. I didn't say this f alpha are non-negative smooth functions. It's noted here. F alpha, non-negative. So partition, it is called partition of unity because the sum of the functions is 1. So they are parts of 1. This is the definition. Okay? And my first result, actually last result, because also we formulate a couple of corollaries of it. But only one theorem about this, which can be formulated in one word, exists. For any open cover of a manifold, there exists a partition of unity subordinated to this cover. So, theorem for every open cover, there exists a partition of unity subordinated to U. Is clear? The statement. I just state that all this exists. We will use it many times in very different, actually, situations for very different purposes. Technically, it's very important mean, and I said last time maybe that this is actually a certain divider. Divider from between C infinity and analytic case. Because certainly analytic functions cannot be like this. They cannot be supported in an open set. If an analytic function is 0 somewhere, then it's 0 everywhere. So proof of this, and I will consider the proof will consist of two parts. First, I suppose that U is locally finite and compact. Locally finite, you remember, I will discuss it. We'll discuss this a lot today. Compact, you remember, every element of this cover, any set in U alpha, has compact closure. Okay? So, how to prove this in this case? Direct construction. I have, you remember, we discussed last time, a theorem that for every open cover like this, there exists a shrinking. You remember. Also, we have an open cover U, we can shrink it to get an open cover V, such that indexes with the same set of indices alpha, and the closure of V alpha is contained in U alpha. I mean, V is also a cover. I apply this twice. I take U, shrink to V, and shrink to W. So U consists of set U alpha, V consists of sets V alpha, and W consists of set W alpha. And V alpha bar is contained in U alpha, W alpha bar is contained in V alpha. Then we apply again our old result, Let me draw it. So this is U alpha. This is V alpha. And this is W alpha. And the sets W alpha as well as V alpha and U alpha cover the whole space. So it may be not visible in this picture, but actually you should imagine that V alpha and W alpha are very close to each other. Then I apply construction, which I already have, and I define a function f alpha, but rather than write g alpha, because f alpha will be different. G alpha, the whole x into 0, 1, smooth. I even do not say this. So that g alpha on V alpha is 1, and G alpha on the complement to U alpha, to V alpha, is 0. Imagine 1 here, 0 here, and something between. This is a locally finite family of functions because the support of G alpha is contained in V alpha and U alpha, so is the family of supports is contained in the family of in the cover, so it is locally finite. Then we can take the sum. Of all these functions G alpha, absolutely. This is some function. This is some non-negative function. I already said to you that this sum is finite everywhere. So it exists, it's smooth. And also, locally, it is a sum of finitely many functions whose values are between 0 and 1. So this is a function, smooth function, positive function. Non-zero. Why is non-zero? Because G is at least 1 on every W alpha. The function G alpha is 1 on 0 on the W alpha. So the whole sum contains a sum which is equal to 1 on W alpha. So it is at least 1 on W alpha, and hence it is strictly positive. If it is positive, then we can divide G alpha over this sum. Maybe better people would say they normalize this family of functions, so I make this division. Now I state that this f alphas is precisely what we need. So this is what we need. Oh yes. It is a locally finite family of functions between 0 and 1. Locally finite family because the support of f alpha is again contained in W alpha, in V alpha, let me say. F alpha is 0 outside of V alpha. So it's a locally finite family. And also the sum of F alpha is 1. So in this case, in this important case, our statement has been proved. This is the most important case. Actually, we will mostly apply this result to the case of locally finite covers, but still let me finish the proof. So what to do if I do not know that my open cover U, given cover, is locally finite? It's just arbitrary. Maybe not locally finite, not compact. So let us turn to the general case. General case. Now U is arbitrary. But we have a theorem, power compactness theorem, which says that there exists a locally finite and compact cover V, which is, well, strongly described in U. So for every V in V, for every element of this covering, there exists an U sub V in U such that V bar is contained in UV. V, you know, is a compact locally finite cover. So for this cover, we already have a partition of unity, right? So there exists a partition of unity F beta, let me say. So my V, let me better use some other. Maybe I will deal without this. So just a function h sub V for every V in V, and these functions satisfy all the conditions. They form locally finite family, and the sum is 1, right? So this is a partition of unity subordinated, however, to V, not to U. Now I want to arrange a partition of unity which is subordinated to U. How to do that? Take a U in U and consider all V's for which UV is UV. Now I define F sub U as the sum over all V's in those partitions such that U sub V is U. And I take the functions HV. So you understand what happens. I have my set U, and there are sets V in my partition, in my cover V, so that this U sub V is U. You see, it's possible that some element of V is contained in several different elements of U. Then I still need to choose some U sub V, maybe one of these two. I choose it arbitrarily, but I have this function. For every V, I fix some U sub V. And then I do this. I claim that Fu is what we need. F sub U is what we need. Yes. You see, the sum is first of all, the sum is well defined. The sum of elements of the partition of HV is defined. And now the sum of Fu, the sum of Fu if this sum over V HV, every HV participates in this sum only precisely once, because every V belongs to is attributed to some U. So we have this property, and F sub U is a partition of unity subordinated to the given open cover. Everything is done. Well, as I said, we will use this theorem for many different purposes, but now I want to give two immediate corollaries of it. You may remember that we had a theorem that if we have a compact set and its neighborhood, then we can arrange smooth functions between 0 and 1, with values between 0 and 1, which is 1 on this compact set and 0 outside of the neighborhood. Now we can say more. Suppose that we have two functions, two sets, f in x and u. This is closed. This is a neighborhood of f. So some set f and a neighborhood of it. This is f, this is u. Then I claim that there exists a function, smooth functions. Smooth function, which is 1 on f and 0 on x minus u. So 0 in the complement of this neighborhood and 1 on f. It can be formulated in a more symmetric way. Assume that you have two closed sets. So equivalent statement. We have two closed sets which are disjoint. Then there exists a smooth function f on x, again with zeros, with the values within the interval 0, 1, such that it is 1 on f1 and 0 on f2. The same statement actually, because just what I need to denote by as u the complement to f2. Just the complement to f2. And I will get the same statement as before. So why this is true, I will prove this in my, well, actually, my proof will be equally good for every of these two statements. Say here, I already have u. Now so again I have f, I have u, which is x, which is which contains f, and I denote as v, x minus f, the complement to f. U and v are two open sets, right? Yeah, right, two open sets. And these two open sets form a cover of x, right? Because the union of u and v is the union of u and x minus f, and it is x because u contains f. Open cover. If so, I can find a partition of unity subordinated to this funny two-element open cover. So I have two functions. F x into 0, 1, g x into 0, 1, f plus g is 1, and the supports are contained in u and v, which means in particular that one of these functions, f, 0 in the complement of this, of V. And I can see now that where f is 0, g is 1, because f plus g is 1. So again, we have f, we have u. I have two functions, f and g. And f is 0 in the complement. G is 0 in the complement. Oh, f is 0 in the complement of f. And f is 0 in the and g is 0 in the g is 0 in u. And by this reason, I deduce that f is 1 on f and 0 on x minus u, precisely what we need. This property, especially in the second statement, is very popular in point set topology, and topological spaces with this property are called normal. Actually, it is terminology is slightly different. A space is normal if two closed sets have disjoint open neighborhoods. And then there is a theorem which is called Ursson lemma, which states that a space is normal if and only if a function like this exists for every two disjoint closed sets. This is so this property is normality, and now we have proved that every manifold is normal. This is actually the best possible properties for topological spaces. There are many separation axioms in topology. How regular and normality is sort of on the top of it, the best property. So from this point of view, if you just want to say something which that sounds well, you can say that manifolds are topological spaces with all the best possible properties. They are normal. And one more corollary of the existence of operation of unity and I want to begin with a question. Suppose that we have a manifold X and we have a function f given, however, so let u be an open set in X and let f be a smooth functions given on u with real values. My question, is it possible to extend this function to a function given on the whole X? What do you think about that? Imagine, you can imagine something simple. Take for X, for example, a line. There exists a smooth function given on some interval, on some open subset of a line. Is it always possible to extend it to a smooth function given on the whole line? A function which is given on an interval, say 0, 1. And I want to extend it to a smooth function given on the whole line. Is it always possible? No, certainly you understand that it is not realistic. Imagine, so I want to extend f to a function, also smooth function given on X. Imagine that you have a function with the graph. This is A, this is B, and the function given on the interval AB. do you really think that it is possible to extend this function to the whole line? No. Somehow it should be infinity here if we want to, if we make this extension. But we can do something sort of less obliging. So theorem, a corollary to my last theorem. For any open set V says that V bar is contained in U, I can find a function G, the whole X into R, says that its extension to V, not to U, is the same as the extension of V, of F to V. Now, if you again look at my picture, I mean this picture, it is very clear how to do it. So imagine that you have a smaller interval, C, D. Then certainly you can find this extension to the whole line. Why not, right? And this is what I want to say, that even if it is impossible, and it is impossible, to extend the function f from u to x, it's possible to do this extension just to require less. We require that this function is the same as before, not on the whole set u, but on some set arbitrary, v, whose closure is contained in u. And this is immediately clear how to do it. I write it here. As before, you find the function h, x into r. So this is u, this is v, and we need some intermediate set. Always possible. And then we find a function, h, x into r. Actually, h is 0 into 0, 1, but it's not important, which is 1 on v and 0 on the complement to w. And we know that's possible. I've just done it. After this, I just take the product. Take h times f. Certainly I can say that f is not defined in the whole x, but h is 0 where f is not defined. So this product does exist everywhere. H is 0 at every point where f is not defined. So this exists. This is a function defined in the whole x, and on v, this is f on v, because h is 1 on v. So this gives us a very important for the future, gives us an opportunity to extend continuous smooth functions from open sets to the whole manifold if we do not insist that the new function coincides with the old function everywhere where the old function is defined. Maybe you need to shrink a bit the domain of f. Then you can do it. I believe that this is all I wanted to say about what? About everything. Open covers, paracompactness, shrinking, partitions of unity. The whole subject now is over. Questions about this? Virgil? Maria? Good. Yes.
This is probably a stupid question, but when we were talking about definition of unity, we first defined functions, and then we add them up, on locally finite compact color, and then we define a new function which is
You mean this construction? You mean this? Before. I see.
Yeah.
Yes?
We divided by G, but why,
yes.
why is it still smooth?
G is a smooth function. G is the sum of functions G alpha. It is smooth, pi is a smooth function. Certainly we can divide. The function inverse to a smooth function is smooth. The product of smooth function is smooth. It is, yes, it is true. If you have doubts, it is good to have doubts, but in this case, I think your doubts can be easily resolved. Certainly it is smooth. We can divide by a positive function. We can divide maybe by a function which has zeros, certainly. But over a positive function, we can divide. Now, my friends, I have some time, and just I want to announce the next subject, which from my point of view, is more interesting. We will consider now tangent vectors to manifolds. And I have questions to you. If I say a tangent vector, do you have any idea what it could be? A vector. A tangent vector to a manifold. A manifold, you know, is something which is defined very much abstractly. Well, let us begin with some simple example. So Rn, or a domain in Rn. A tangent vector to Rn is what you call a vector. You do not say this, but you mean this, that a vector is an arrow. An arrow which maybe is attached to some point. In the Euclidean space, a vector is an arrow. So we have a point in the Euclidean space. We draw an arrow which starts at this point. We call it a vector. We can call it a tangent vector to the Euclidean space because the word tangent by itself doesn't mean anything. But this definition, which is certainly quite understandable and good for in the case of Euclidean space or domain to the Euclidean space, becomes sort of less clear if you consider a manifold, even such a manifold as a sphere, or, well, even simple example, which is not Euclidean space. What we have now, we have sort of analysis on manifolds. Smooth functions, you know, ring of smooth functions, we can multiply them, add them. And is it possible to relate somehow vectors in space, well, in Rn, to functions? And this is a part of calculus, which maybe not only you study, but also teach. If you have a vector, then what can you do with the function? What was the vector? You have here a point and some vector at this point. Suppose you also have a function on your manifold. What can you do if you have a vector? And this your students in calculus will answer immediately. We can take the directional derivative, right? If there is a vector, then we can take the derivative associated to this vector. You understand? Take your point P, then move, attach to it the vector epsilon times the given vector V. New point, take the difference between the two values of the function, divided by epsilon, and take the limit when epsilon goes to 0. For vectors, we have directional derivatives, which have some algebraic properties. And these properties can be formulated in the language which we have for manifolds, which certainly gives you some at least idea, some approach to tangent vectors to a manifold. I will give you a precise definition But let me first, I want to be frank with you. If you take 5 different books in differential topology and just look for a definition of a tangent vector, maybe you will find 5 different definitions. Because there are several equivalent approaches to tangent vectors. What I am going to do, from my point of view, is the most frank. I define tangent vector precisely as I need to apply it, as need for applications. And then we will see that it is equivalent to any other approach to tangent vectors. So, definition. Let X be a manifold, and let P be a point. A tangent vector Xi at P is a linear map of the space of all smooth functions on your manifold. It is a vector space, C infinity M, because there are functions. You can add them, you can multiply them by numbers. It is a vector space. R is also a vector space. I mean, real vector spaces, and there are linear functions, which satisfies the following condition. Says that if f and g are 2 functions, absolutely arbitrary smooth functions, Xi is defined for every function. So Xi applied to fg, this should be a number, right? Is equal to Xi of f times g of p plus f of p times Xi of g. Please don't say to me, because I will not believe anyhow, that this condition surprises you. This is the usual product rule. This is always applied to derivatives. So this Xi of f should be regarded as something similar to a derivative of our function at the point p. The point p means that actually we use here the value at p, not because the left-hand side is a number. So the right-hand side also should be a number. And we have this condition. That's all. This is my definition of a tangent vector. I just to finish this story today, I want to discuss with 2 things. First, is it clear to you that tangent vectors at P form a vector space? We can add 2 such maps, and it will be a map which satisfies the same condition. You can multiply this map by a number again. So this is a vector space. The space of all tangent vectors to the manifold X at P. What's the estimate? What is the dimension of this space? So we have vector space T. The usual notation is T sub P X. To X at P. Since you don't want to say, I will say. I will say first what I expect that you say. Then I will say, no, this is wrong, and say what is right. So the definition is such that it seems like something very huge. And you can expect that the dimension is infinity. This is an infinite space. Actually, this is wrong. This is an n-dimensional space, precisely as your manifold. Thank you for your patience. attention. So see you. Monday will return the homeworks to you and expect that you will solve more problems on Monday.